This week our focus is using Matlab to do 1D and 2D interpolation of data. When using interpolation, our first question is going to be, what is interpolation? So interpolation is fairly similar to fitting, which we did a couple of weeks ago, where we're going to have collected data or experimental data, and one thing we want to do with that is, quote, fill in the missing pieces. So like we did with curve fitting, maybe we're taking data and we're taking data every 1 minute, but we want to make really an estimate as to what was happening every half minute, the times that we were not measuring. Or maybe we're taking a sample of, say, population every year, and 1 year for some reason we were unable to collect data. We can use interpolation to make an estimate as to that year that we missed in our data collection. But how is interpolation different than curve fitting? In curve fitting, we either had an idea of the curve that should fit our data, so if it was something like a capacitor, we know that it should have an exponential decay, or if it was something like population growth, we might think, oh, we want to use an exponential growth to fit that data. Or, again, if we have some other constitutive relationship, that gives us a clue of what curve to fit. Or we can look at the shape of the data and kind of come up with what curve looks like it would best fit the data. And we put it through the fit and we can get some equation, some parameters, that if we have our independent variable, we're able to figure out what our dependent variable is. Interpolation works differently. We're not trying to come up with one equation that describes all of the data that we collected, but basically it works like a table lookup where we're going to find a point that we're interested in knowing our dependent variable, and we're going to look at least in one dimension, what is the point to the left of it, and what is the point to the right of it, and then we're going to use that information to figure out what's happening between those two known points. And we're going to be looking at linear interpolation and cubic interpolation in this course, although there are other methods as well. And unlike the curve fitting, interpolation will always give us back our original points because we're only looking at what happens between collected data points. If it's on a collected data point, then we know empirically what happened. This is different than curve fitting, where the curve doesn't necessarily go through all of your original data points. And in contrast to when we're doing fitting before, for example, for that anthropometric data, where we had a lot of data points from collecting people's heights and people's arm lengths, for example, we could put a fit in that said if we knew their height, we could predict what their arm length was using that fit command, and maybe we use a linear fit. Interpolation, that's not going to work for us. This is only good if we're running a single experiment. We don't want what I'll call statistical data or a lot of samples around that same point. This is only good for one experiment, and we'll see what that type of data looks like. Similar to the warning I gave about using a fit or a curve fit, it's best to only measure points or estimate points between data that we actually collected, and that's what interpolation is. If we're, say, only collecting data for 10 seconds and we want to make an estimate as what happens at 11 seconds, that will be what we call extrapolation. We're going outside of the range of the data that we originally collected. So if we're in between data points we actually collected, it's interpolation, and that's okay to use. If we're outside our collected range, it's extrapolation, and in this course we're not going to cover that because often extrapolation can lead to errors in our estimation. Now, to effectively use interpolation or even a curve fit, we need enough original data so that we can make a good estimate as to what's happening between those data points. So if you remember all the way back to the first homework where we looked at that vibration problem, when we only used a couple of points to describe that trig function, it didn't look at all like a sinusoidal wave or some sort of periodic function. But the more and more data that we collected, the more, or samples that we used, the more it looked like the original function. The same is true when we have experimental data. If we're collecting it too infrequently, and if we try to use linear interpolation, our estimate is going to be way, way off. So basically, if something is oscillating at some frequency, we need to sample at a higher rate than that frequency is in order to adequately construct the shape of the original data. So again, the higher frequency something is oscillating or changing, we need to sample that much more frequently in order to have a dense enough collection of data so that our estimates are good.